Hello, good morning. I thought I'd try to teach you a little differential equations this morning. Cal 2 starts with this chapter 6. It does a little mini version of differential equations. Differential equations is a whole course. There's another course called Advanced Differential Equations. There's another course called Partial Differential Equations. So it's a big, broad subject, but in the beginning of Cal 2, chapter 6, we do a little mini chapter here, and I even sort of abridge that chapter a little bit. So a differential equation is an equation with a derivative in it. And like I said, there's millions of courses. There's a few courses about this, and so they can get quite complicated. So this is fairly simple, and we're going to learn one technique how to solve these. This is an equation with a derivative in it, and the technique we're going to use is called separation of variables. Separation of variables. Sometimes I call that separation of variables. Sometimes I call it separate and integrate. Separate and integrate. I'm not sure if I'm spelling that right. That's okay. So what you do is you take the y prime and you write it as dy dx. That's kind of an important part of this. So that's an alternative form to write the derivative. You know that. And then you separate the variables. So you try to get the dx over here with all the x's, and you try to get the y over here with the dy's. So you get the y's with the dy, you get the x's with the dx, and you get it separated. Now I know there's no x's here, but what you do then is you kind of multiply both sides by dx, and that moves the dx over here. If there was some x's here, I'd leave them here with the dx. I want to divide by y, so I take this y and I divide by y. So maybe you can, that's a couple algebra moves there, and I get this. So separating the dy dx and separating the other variables is the separate move. And sometimes that can get complicated. It's just algebra though, but that's the separate part of this. And that was not a difficult one. And so now you integrate. And so on this side, you're integrating with respect to the variable y. And everybody knows to integrate a 1 over y dy, you get the natural log of y. You integrate this side. The step is you integrate both sides, sorry. And you integrate this side with respect to y, and you integrate this side with respect to x. I guess we get a negative 0.25x plus c. Now you may have wondered, why didn't I put a plus c here? And I could have. And it would have been a different c than that c, and then I would have moved this c over and kind of let it absorb into that. You know, these arbitrary constants can kind of absorb into each other. So anyway, I could have had a c1 and a c2. I could have subtracted the c1 from the c2 and called it a c. It's an arbitrary c. So I never put it over here. I always put it with the x's. Well, that's it. And, you know, in a way, we solve the differential equation. That's what we're trying to do. We're trying to solve the differential equation. And what that means is find the function y. So this is a differential equation. We're solving it by trying to find the function y. Now, we have the y and x relationship. Right now, it's called an implicit relationship. What we'd like to have is y all by itself, so we want what's called an explicit relationship. We want y explicitly in terms of x. A lot of language here. But there are some problems where they stop here and they circle it and say that's your answer. And if I did that, I'm not going to do that, but if I did that, I would call that an implicit general solution. This is called a general solution of the differential equation, but it's an implicit general solution because we haven't solved for y. Okay, let's solve for y. Everybody knows how to solve for y. You e both sides. And there's some interesting algebra here, but the e and the log cancel each other out, and I'm left with y. And I dropped the absolute value at this point. My explanation would be e to the anything is positive. So there's no way that this y is going to be negative. So it's redundant to have the absolute value. so anyway, e to the log y cancels, and I get rid of the absolute value. On this side, there it is, it's e to that whole thing. And what you don't do is e each term, that's bad algebra, but watch this. If it's e to the negative 0.25x plus c, I can write it like this. E to the negative 0.25x times e to the c. Because you know, in algebra, when you multiply like bases, you add the exponents. So if I was multiplying these bases, I would add the exponents and get this. What I'm doing is the opposite of that. I'm doing that backwards. And then, again, because the c is an arbitrary c, I can call that e to the c. E is just a number. I can call that e to the c a c. It's a different c than it was, but that's okay. Here I am with the answer. Y equals c, I'm calling that c, multiplied by e to the negative 0.25x. And I'm going to circle that, and I'm going to call that an explicit general solution. An explicit general solution, which is usually what I'm after. Sometimes we want to leave it implicit, but if we can solve for y, we do. That's what I like to do. And that's classic. If I try to draw a picture of that, it's kind of funny to draw a picture because it's got this arbitrary c. And so the picture is not just one function, it's sort of what we would call a family of functions. But it is, depending on the c, it's an exponential decaying function with that negative 0.25x. It's an exponential decay rather than exponential growth. And so, I don't know, if c was a 1, it would be this picture. If c was a 2, it would be this picture. If c was a 3, it would be this picture. If c was a 10, it would be this picture. So, you know, it's a whole family of functions. If c was negative, what happens if c's negative? I think it would be this picture. But again, I don't think c, usually in our application problems, c is not negative. But it's a whole family of functions, this general solution. I'm trying to graph it for different possible values of c, and I get this whole family of functions. All right, I'm going to keep talking. We're going to learn some stuff here. If sometimes these differential equations come with an initial value, meaning they say this, y of 0 equals 3. Or when x is 0, y is 3. Or, it goes through the point 0, 3. There's a lot of ways to say that. And I'm sort of using a funny function notation. Instead of a function notation f of x, I'm kind of calling this y of x. Okay? And so anyway, when x is 0, y is 3. It goes through the point 0, 3. Or y of 0 equals 3 is called my initial condition, or my initial value, or my initial condition. And when that's given to me, then what they're saying is, I don't really want this general family of functions. I don't want this general solution. I want you to find the specific member of the family that goes through this point 0, 3. If that was a 3. So we're looking for this solution that goes through the point 0, 3. We're looking for what we call a particular solution, not a general solution, but a particular solution. And what that means is, you can, at the end of this problem, you do all this work the same, but with this initial value, you plug it in for x and y, you plug it in for x and y, and you find c. Finding c makes it now a particular solution. One particular member of this family of solutions. So it's easy. And again, you're learning a lot of language here, but I'm plugging in a 0 for the x, I'm plugging in a 3 for the y. I'm going to do that right here. 3 for y, 0 for x. Guess what e to the 0 is? E to the 0 is a 1. Guess what? So c is 3 in this particular case. The c is not always that number, but in this particular case it is. So I'm going to write this now. Y equals 3 e to the negative 0.25x. I'm going to circle it, and I'm going to call it a explicit. It is explicit because I solved for y, but this time it's a particular solution. Particular solution instead of a general solution. I use the initial value or initial condition to find c. That means I found a particular solution, and it's this one particular member of this family. So that's a lot of language. Solving a differential equation with this method, separate and integrate, separation of variables. You could stop and have an implicit general solution, but it's better to solve for y and get an explicit general solution, which is a whole family of functions. But if you have an initial value or initial condition, you can plug it in to find c, and if you find c, then you don't have a general solution, you have a particular solution. And it can be explicit or implicit, I suppose, but we like an explicit solution if we can get it, solve for y. And then that's just one graph, just one graph. That's an exponential decaying curve. Yeah, that's a lot of stuff. That's good. That's good. Now, to me, that's how differential equations starts, learning all this terminology and language, but the book starts a little different. So I'm kind of 6'2", 6'3", and if I'm in 6'1", they talk a little different there at the beginning of this chapter. But to me, this is how you present this topic. So good luck.